And thanks for joining me today. In the previous two videos, we talked about the kinetic molecular theory and the named or alphabet gas laws. Today we're going to start talking about how we put all those together, the combined gas law and the ideal gas law. So let's review those named gases real quick. Avogadro's law gives us the pressure and temperature are constant and that moles and the volumes are directly proportional. So it's a direct relationship. Then we have Boyle's law, which in Boyle's law, moles and temperature are constant and the pressure and volume are inversely proportional. Then we have Charles' law, where the pressure and moles are constant and volume and temperature are directly proportional. In Gay-Lussac's law, we have volume and moles are constant and pressure and temperature are directly proportional. Dalton's law is not part of this discussion, but with these four named laws, something is constant in each one of them. At least two variables are constant in each one and two variables change. But what if none of the variables are constant? If none of our variables are constant, then we can't use any of those individual laws. So that's where the combined gas law comes in. It shows the relationship between all four gas properties in one equation. It's sometimes referred to as the changing gas law because all of the variables change, and it's dealing with a situation of before and after. So when there is a change between our starting point and our ending point, something is changing, and so it is the changing gas law. Now this is a combination of all four of them. Technically all four of those gas laws are changing gas laws because it's a before and after situation, and so this is the combined changing gas law. Now the combined gas law states that the volume of a gas is directly proportional to the absolute temperature and the amount of gas, or moles, and is inversely proportional to the pressure exerted by the gas. So it's directly proportional to the temperature and moles and inversely proportional to the gas. Now, as we learned when we talked about the other ones, a direct relationship means we're going to be dividing, and a inverse relationship means there's a multiplication there. So that gives us the equation P1V1, because our pressure and our volume are inversely proportional, divided by N1T1. So we have our pressure and pressure and volume are inversely proportional, so they're on the same side, and we're dividing by the number of moles and the temperature. And that's going to equal to P2V2 over N2T2. So one of the laws, we didn't talk about a law that dealt with this, but you'll notice that that means that the number of moles and your temperature are actually inversely related because they're both being multiplied. Yes, they're in the denominator, but they're being multiplied by each other. So the number of moles and the temperature are inversely related. But this is the equation for the combined gas law. So let's look at an example problem in which we're dealing with all four of these variables and all of them are changing, and how we would do this, plugging in and doing the math for this particular type of situation. All right, so for the combined gas law, again, we've got to remember that everything is going to be changing. So we're going to write things down as they go, giving them the numbers. So a 2.50 mole sample, so that is going to be my N1 is 2.50 moles. Of a gas is held at 2.70 atmospheres. So P1 is 2.70 atmospheres of pressure and has a volume of 23.3 liters. So V1 is 23.3 liters when the temperature is 306.5 Kelvin. So T1 is 306.5 Kelvin. When the temperature is decreased to 150.0 Kelvin, so T2 is 150.0 Kelvin, gas is released from the container, causing the volume to decrease to 10 liters. So my volume is going to decrease to 10, and I'm going to say that that was 10.0 liters. I think that's what I intended to type, sorry. And the pressure to decrease to 1.98 atmospheres. So P2 is 1.98 atmospheres. How many moles of gas are left in the container? So N2 is what we are looking for. So again, we're going to start off with our full equation. We have P1 times V1 divided by N1 times T1 is equal to P2 times V2 divided by N2 times T2. So if I want to find N2, first thing I'm going to do, again, even though that these are multiplied together, this is still just a proportion, just like all the named gas laws we did in the other video. So I'm still going to just cross multiply. And when I cross multiply that, that's going to give me P1 times V1 times N2 times T2. So I multiplied these two together, equals P2 times V2, and I'm multiplying this by N1 times T1. And since we're multiplying, we just put them all together. Now, if I'm trying to find N2, N2 is right here. So I need to get these three things to move over to the other side, and I do that by dividing. So I'm going to divide by P1 and V1 and T2. And so the P1s are going to cancel, V1s will cancel, T2s will cancel, and over here I'll be left with N2. And so then I'm still going to have my P2, V2 times N1 times T1, but now I divided by P1 times V1 times T2. So this is our full finished equation. So now I'm going to plug in numbers. So P2 was 1.98, and just because of space, I'm going to leave off the units here. V2 was 10.0. N1 is 2.50. And T1 is 306.5. And sorry, I went off the screen a little bit. Let me move this over just a tad. So that's my top, and now I'm going to divide by P1 is 2.70, and V1 is 23.3, and then T2 is 150. So now I simply plugged in all of my numbers. So I'm going to take my calculator, and I'm just going to multiply this all together. Now it's helpful if you just put these in parentheses. So I'm going to put the top in parentheses. So I have 1.98 times 10.0 times 2.50 times 306.5. That's my top. And divide that by the bottom in parentheses, 2.70 times 23.3 times 150. And I get an answer of N2 is equal to 1.6077. Well, look at the numbers I started with. I have 3 sig figs, 3 sig figs, 3 sig figs, 4 sig figs, 3 sig figs, 3 sig figs, 4 sig figs. So I want my answer to have 3 sig figs. So that's going to round that to N2 is equal to 1.61 moles. And there we go. That is the combined gas law. I realize that there's a lot of numbers here, but it's really not any more difficult than all of the others. You're just doing solving a proportion, just like you would have done in math a couple years ago when you first learned how to do proportions. So there's that one. Okay, so we've seen an example where everything is changing, but how are these named gas laws just special cases of the combined gas law? Because why would we have to know all 4 of those other gas laws if we have the combined gas law? The combined gas law has all of them. And the combined gas law actually is a combination of all the other 4. So all the other 4 are special cases. Or we can take the combined gas law and bring it on down to any of those individual gas laws. So you see here that you've got the equation for the combined gas law. And one thing you need to know is we're dealing with multiplication and division. So when you're solving these, if you have a number that is exactly the same on the left side of your equation and the right side of your equation, then that term can be taken out. It can be ignored. It can be dropped out of the equation, because when you actually do the algebra to solve the problem, they're going to cancel out anyway, because you're going to be dividing one by the other, and it's going to become 1. It's going to go away. So if a variable is constant, that means it's the same on both sides of the equation, so we just take it out. So let's just say that we have a situation where your number of moles and your temperature are constant. Well, if your number of moles and your temperature are constant, then they're going to go away and be taken out of the equation. And then you're going to be left with P1 V1 equals P2 V2, which is Boyle's law. So Boyle's law is simply a case of the combined gas law where number of moles and your temperature are constant. Back to the combined gas law. So what if instead of number of moles and temperature being constant, what if we take our pressure and our number of moles, and those are constant? Well, if our pressure and number of moles are constant, we're left with V1 over T1 equals V2 over T2, which is Charles' law. So you see that Charles' law is a special case of the combined gas law also. And we can do the same thing if we take our volume and our number of moles and make those constant. If our volume and number of moles are constant, then we're left with Gay-Lussac's law, where pressure and temperature are directly proportional. And of course, you can do the same thing to get Avogadro's law. If our pressure and temperature are constant, then we have a direct relationship between volume and number of moles, and that, of course, is Avogadro's law. So our combined gas law is simply a combination of all of the other 4 laws. And really, you do need to understand the names and the definitions and what's constant in each of those other laws. But when it comes to actually working out problems, the only equation you actually need is the combined gas law equation, as long as you understand that if a variable is constant, it just gets taken out of the equation. And so the only equation you actually have to know is the combined gas law equation. But the combined gas law deals with situations that's changing. I have a before and an after, so there's a change happening. What if I don't want to know a change? What if I just want to know a situation? So let's say I need to create something that will hold a gas at a certain volume and pressure. I need to know what I need to build and how it needs to work. And for that, we use the ideal gas law. Now, the combined or changing gas law, again, used to find the value of a variable when something is changing. We don't want to change anything, and we just need to know the value of one variable given a certain set of conditions. Then we use the ideal gas law. Before we get into the ideal gas law, we need to discuss what an ideal gas is. So an ideal gas is a gas in which the individual particles have negligible size, or their point particles, we ignore their volume, the individual particle volume. They do not interact with other particles other than in collisions, and all collisions are 100% elastic. So basically, these are the postulates of the kinetic molecular theory we talked about a couple videos ago. So an ideal gas exhibits all of the postulates of the kinetic molecular theory. The problem is that real gases are not ideal. Real gases do not behave exactly that way, but they do behave close enough at normal scale in normal situations with normal pressures and normal temperatures. They behave close enough that we can use the ideal definition to actually do our calculations. In fact, the only gases that truly do exhibit pretty much an ideal gas situation would be the 6 noble gases. They're the only ones that are going to follow along with the ideal definition best, because all other gases are going to have some electrostatic interaction between the particles because of electronegativities and molecule shapes and stuff like that, which we're not going to get into. So the ideal gas law states that the pressure of an ideal gas is directly proportional to the amount of gas and the absolute temperature, and inversely proportional to the volume of the gas. So pressure is inversely proportional to volume and directly proportional to moles and temperature. But the thing is in order to get an exact value, we have developed what is called a proportionality constant. We figured this out through all of our experimentations and data, and we have a proportionality constant that is called the ideal gas constant. The ideal gas constant in the equation is recognized with a capital R. So R is the ideal gas constant. That's a proportionality constant in the ideal gas law, and its value depends on what the pressure is measured in. So we're going to have different values for R depending on how we measure the pressure. And if we measure our pressure in atmospheres, the value for R is 0.0821. If we measure our pressure in kilopascals, then the value for R is 8.31. And if you measure your pressure in millimeters of mercury, then the value for R is 62.4. Notice the units are the same. It's liters times atmospheres divided by moles Kelvin. Liters times kilopascals divided by moles times Kelvin. Liters times millimeters mercury divided by moles times Kelvin. The units are the same except for the unit of pressure. So whatever unit your pressure is measured in, that will determine which version of R you're going to use in the equation. And you'll see that when we do a couple of examples. So the ideal gas law equation is as follows. Remember, if pressure is inversely proportional to volume, they're multiplied and going to be on the same side of the equation. And if it's they're inversely proportional, pressure and volume are inversely proportional, so direct proportionality means they're going to be on opposite sides of the equation. And so we've got N, our proportionality constant R, and T, our temperature. So this is the ideal gas law equation. PV equals nRT. You'll often hear a lot of chemists and physicists refer to this as PIV-NERT, because that's kind of what it looks like when you read it, PIV-NERT. So PIV-NERT is a reference to the ideal gas law. So let's look at some examples of using the ideal gas law in calculations. All right, in this example, 35 moles of oxygen are placed in a container, so N equals 35 moles, are placed in a container at 20 atmospheres, so pressure is 20.0 atmospheres. If the temperature of the container is 20 degrees Celsius, so T equals 20 degrees Celsius, what is its volume? V equals question mark. Now, I do know that I'm going to have to use the ideal gas constant, R, and since my pressure unit is atmospheres, I'm going to use the value of R that has atmospheres in the unit, so that's 0.0821, and the unit for that is liters times atmospheres divided by moles times Kelvin. That's the full unit. So this is all of the data, all of the information for my question, but I do need to know, make sure we remember that you have to have your temperature in kelvins. So I'm going to have to add 273 and get this to be 293 kelvins. We cannot use Celsius temperature in this. Notice the unit here is Kelvin. Temperature has to be in Kelvin also. So PV equals nRT, and I'm solving for V. So really all I have to do is get V by itself. So I'm going to divide both sides by P. And that gets rid of the P over here, leaving me with V equals nRT over P. So now I can plug in my numbers. So V is going to equal my N, which is 35, times R, 0.0821, times T, 293, divided by my P of 20.0. So now I put in my calculator, 35 times 0.0821 times 293 divided by 20, and I get an answer of V equals 42.09. Now, this is only 2 sig figs, so my answer needs to have only 2 sig figs, so V equals 42, and this is my unit of volume, so that would be 42 liters. So there is the use of the ideal gas law, and how do you pick which ideal gas constant to use all depends on which pressure unit you're using. 6.8 moles of air, so N equals 6.8 moles, are placed in a container at 300 Kelvin, so temperature is 300 Kelvin. If the volume of the container, so volume of the container is 3.9 liters, what is the pressure? So what is the pressure in millimeters of mercury? So I want it to be in millimeters of mercury. And so I need to know which R value I'm going to use. Well, I have to use the R value that has millimeters of mercury. So that is 62.4 liters times millimeters of mercury divided by moles times kelvins. That's the unit. All right, so PV equals nRT. I'm solving for pressure this time, so I'm going to divide by volume on both sides, giving me pressure equals nRT divided by V. I can now plug in my numbers, so P equals N 6.8 times R 62.4 times T 300 divided by V 3.9. So then I just put this in my calculator, 6.8 times 62.4 times 300 divided by 3.9, and I get an answer of my pressure is 32,640 millimeters of mercury, but this is only one significant figure. Notice I started off with only one sig fig, so I need to have this be only one significant figure. So I need to round that to 30,000 millimeters of mercury. That is a very unreasonable pressure, because if you were to actually have a barometer, that would be 30 kilometers tall. Unreasonable, but I made up these numbers, so that's how it works. All right, 3.0 moles of air. So again, N equals 3.0 moles are placed in a 0.75 liter container. So volume is 0.75 liters at 300 kPa. So my pressure is 300 kilopascals. What is the Celsius temperature? So now I want to know the temperature, and I need it to be in Celsius. Remember, when we solve this, we're going to get our temperature in Kelvin, so we're going to have to convert it to Celsius afterwards. And I need to know which R value to use. So my R value is going to be from the kilopascals. My pressure tells me which R value to use. So I'm going to use the R value of 8.31 liters times kPa over moles times kelvins. So PV equals nRT is our equation. This time we're looking at this side. If I'm solving for T, I need to divide both sides by N and R. So divide both sides by N and R so that the N and the R cancel, and I am left with T equals P times V over N times R. So then I can plug in my numbers. T is going to equal 300 kPa times 0.75 liters divided by 3.0 moles times 8.31 is our R value. So we have 300 times 0.75 divided by 3 divided by 8.31, and that gives us an answer of 9.025. It's 9.025 kelvins. I need this to be in Celsius, so I'm going to subtract 273 from that, and that gives me a Celsius temperature of negative 263.97 degrees Celsius. But now we have to convert to proper significant figures. I only had one significant figure here, so this has to have only one significant figure. So my final temperature is negative 300 degrees Celsius. And that's that one. So after seeing those examples of the combined gas law and examples of the ideal gas law, hopefully you can see that those two equations are really the ones that are the most important. those named gas laws, you need to know them and understand how they work, but the combined gas law equation, P1 V1 over N1 T1 equals P2 V2 over N2 T2, that equation, and PV equals nRT, that equation, the combined gas law equation and the ideal gas law equation are the only two equations that you're really going to need when solving any of these problems. And that's how gas laws are awesome, because it's all really just a matter of plugging into the equation and solving the problem, and it's not super complicated. So hopefully you enjoyed this and you understand after seeing the examples. Thanks for watching, and have a day.